Okay, so we're going to transition a little bit and talk a little bit about data transfer and how things like Wi-Fi and your cell phone work. So how do we get data from one place to another, seemingly through the air? Now, in order to do that, we need to have a little basic understanding of how computers work and how they store information. So we're going to talk a little bit about binary numbers. So at the end of this lesson, you should be able to explain what a binary number is, explain the difference between a binary number and a decimal number, convert decimal numbers to binary, convert binary numbers to decimal, and then also convert letters to binary and vice versa. So what does binary mean? The binary number system is a method of representing numbers by using combinations of only two numerals. Okay, we typically see this written as 0 and 1. This is also called the base 2 number system. So let's talk about our number system for a little bit. Okay, so what is a decimal number? When we say a decimal number, what we typically think of as a number, what do we count by? So we use what's called a base 10 numbering system. Each place value has 10 times the value of the place to the right. So for instance, this 9 is in what we call the ones place. So what that means is that 9 represents 9 groups of one thing, whatever we're talking about. The 5 is in the tens place. So what does this mean? It means that there are 5 packets of 10 represented by this number. The 3 is in the hundreds place. So it is representing 3 packets of 100. And then the 2 is in the thousands place and therefore represents a value of 2 packets, each with 1,000 in them. So when we say the number 2,359, what we mean is we have 2 packets of 1,000, we have 3 packets of 100, 5 packets of 10, and 9 packets of 1. And if we were to count all of those pieces, that's what we would call 2,059. So as we add numbers to the left, the place value increases by a 10 from the one just to its right. So we can write this in terms of powers of 10. The ones place is 10 to the 0 power. What is anything to the 0 power? It represents ones, right? So if we move to the tens place, this is representing 10 to the first power. The hundreds place is 10 to the second, and the thousands place is 10 to the third. So when we say a base 10 number system, what we mean is each place in the number represents a power of 10. So here's what's different. So bi means 2, right? So a binary number system is based on a multiple of 2. So each position of the number represents a power of 2. So we're going to start over here on the right and look at the first symbol. The first position represents 2 to the 0 power. Again, anything to the 0 power is 1. And so the first position counts 1. The next position represents 2 to the first power. Okay, so 2 to the first power is 2. So the second position represents a count of 2. And then we have 2 to the second, which is 4. So the third position represents a count of 4. Next comes 2 to the third, or 8. And then 2 to the fourth, or 16. Got my numbers. And then 2 to the fifth is 32. And just like our base 10 number system, we can continue on for however many numbers that we need. Each position in the number is represented by either a 0 or a 1. These ones and zeros are not the number 1 and 0, but a symbol to represent whether the place value is counted or not. We call these bits, which is a term that is short for binary digits. A bit usually is represented in a computer's main memory by a transistor that is switched on or off, or a capacitor that is charged or discharged. So the 1 and the 0 represents the state of the computer system. So 1 means that the position is turned on. 0 means that the position is turned off. So looking at this first bit here, it is a 0. So that means that we will not count the 1. If we look at the 2 position has a 1, which means it is turned on. So we will count the 2. The 4's place has a 0. This means that it is not turned on, so we will not count the 4. The 8's place bit is 1, which means it's turned on, so we will count the 8. The bit in the 16's place is 0, so skip that one. And then the last bit is 32, and it is on, so we will count that as well. From here, we just add up all the numbers. So 32 plus 8 plus 2 equals 42. So the binary number 101010 represents the number 42. So if we look at this binary number, we have 001110. The 1's position is turned off, so we will not count the 1. The 2's position is turned on, so we will count the 2. So is the 4's position. So is the 8's position. So those 1's represent the 8, 4, and 2 that are turned on. When we add those numbers together, we get 14. So what about this one? 100111. The 1's position in this case is turned on. So is the 2's position. And so is the 4's position. We're going to skip the 8 and the 16 since those are zeros and those would be turned off. We're not going to count them. But the 32 is turned on. So 32 plus 4 plus 2 plus 1 is going to be 39. All right, so pause your video. Convert these numbers into binary. So if we look at this first one, this first position is the 1. It's going to be turned on. The second position is the 2. It will also be turned on. The third and the fourth position, the 4 and the 8, are turned off, but the 16 is turned on. So we're going to take 16 plus 2 plus 1, and that gives us the number 19. For the second one, the 1 is turned on. The 2, 4, 8, and 16 are turned off, but the 32 is turned on. So 32 plus 1 gives us 33. This third one, the 1 is turned off, the 2 is turned on. The 4 is turned off, the 8 is turned on. The 16 is turned off, the 32 is turned on. Okay, now what about these other two? Remember, they just start doubling. So we would have 64 and 128. So 128 plus 32 plus 8 plus 2 is going to give us 170. The fourth one, the 1 and the 2 are turned on. The 4 is turned off. The 8 and the 16 are turned on. So we end up with 16 plus 8 plus 2 plus 1 is 27. This last one, the 1, 2, 4, 8, 16, 32, and 64 are all turned on. So we would add up 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, and we're going to get 127. All right, now what if you want to go in reverse? What if you have a number and you want to convert it into binary? You could write out those numbers and just kind of guess and check, but there is a little bit easier way to go about that. So what you're going to do is you're going to take your number. This is our decimal number 97, and we're going to divide it by 2. 97 divided by 2 is 48 with a remainder of 1. So we're going to write out 48 and put a 1 over here on the side. We're going to do the same thing with a 48. Now 48 is divisible by 2, right? We get 24 and there's no remainder. So we're going to put a 0 over on the side. We're going to take 24 and divide it by 2. Again, this is an even number, so we're not going to have a remainder. So we're going to write a 0 over on the right. Then we're going to take that 12 and divide it by 2. Again, even number, so it has a remainder of 0. Now we're down to 6, divide by 2. That gives us 3 with a remainder of 0. Now 3 divided by 2 is 1 with a remainder of 0, or a remainder of 1. Sorry, got on a roll there. Okay, so 3 divided by 2 is 1 with a remainder of 1. So we're going to write a 1 over on the side. Okay, now this is where it gets a little bit weird. So we're going to take 1 divided by 2, which is 0, right? Now we're down to 0. But there's a remainder of 1 left over. So what we have over here on the right is whether or not we have a remainder. We are going to read that from the bottom to write our number. So 1100001 represents the decimal number 97. So pause for a minute and convert these decimal numbers into binary. All right, so if we take 17, divided by 2, if you go through that whole process, we're going to get that 16 position turned on, along with the 1 position turned on. So 10001 is the binary number for 17. 25 will be 11001. So the 1's position, the 8 position, and the 16 position are all turned on. 43 will have the 1, 2, 8, and 32 position turned on. 85 will have the 1, 4, 16, 64 turned on. And then the 1312 will be 1011 or 100100000. I can't remember what those positions are. I'd have to write those out. I'm not very good at doing this in my head, so we're going to go with that. Do you get it? Do you get it? If you don't get this yet, maybe go back and review the video and see what it is that you're missing. So we can also use these symbols to represent letters. And what I kind of want to reiterate is those 1s and 0s are not 1s and not 0s, but they're representing whether or not those positions are turned on. There are other types of binary codes out there. If you think about Braille, Braille is a binary, right? Is that position turned on? Is it punched up? Or is it left flat? So when you look at that series of the punches, it tells you certain symbols. The same thing with Morse code. Dots and dashes represent different codes, right? So the dot could be our 0, the dash could be our 1, or vice versa. It doesn't really matter. But those different combinations of those things represent information, whether they're turned on or turned off. So any code that uses just 2 symbols to represent information can be considered a binary code. And it does not have to be 1s and 0s. It can be punches, it can be dashes, it could be dots. There's all kinds of things that you can use for that. So letters and symbols have their own binary code. Computers do not read letters. They don't read numbers. They read binary. So if you think about all of the things, when you press a button on your computer, press the A button. Your computer doesn't read that as A, but it reads it as a series of 0s and 1s, or the binary symbol for A. So you have a sheet that looks like this binary text conversion sheet. It has all of the codes for the capital and lowercase letters, along with some symbols. Using that sheet, decode this question. What do you call a duck that gets all A's? Pause your video and decode it. See if you can come up with the answer. You call him a wisecracker. So notice that the capital letters start with 010, and the lowercase letters start with 011. That's kind of something to help you narrow down where to find those letters. Also notice that there is a binary code for the exclamation point. Okay, now try this one. How can you tell a vampire has a cold? Pause your video and decode that. They start coughing. All right, so that is an overview of the binary number system and how we can convert numbers and letters into binary and vice versa.